Welcome. On this video, we're going to be discussing how do we properly solve logarithmic equations. So let's get started. Before we go into the actual examples, let's just review this key property for logarithms. Remember that we can express logarithmic equations as exponential equations. And how do we do that? Well, this is just a very basic logarithmic equations. Here we have y equals log of base b evaluated at x. And remember that we can express this expression as exponentials. We can get the base of the log and make it the base of an exponent. And the exponent is what's going to be equal, which in this case it is y. And now the exponential expression, it's always going to be equal to what's inside the log, which in this case is x. And remember that we always have this triangular thing going on. So b to the y equals to x. And this is how we can go back and forward between logarithm equations and exponential equations. And we're going to be using this property. We're going to take advantage of this property to properly solve log equations. So let's get started. Here we have a couple of examples, and let's just go one by one. So what we want to do is we want to solve the following equations. Notice that this is a logarithm equation since there's a log involved and the variable that we're looking for is inside the log. So how do we properly get x by itself? How do we isolate x? X is inside the log, so somehow we need to get rid of the log. We have one way to get rid of the log, and that is to use a property that we just discussed here. Because now, in example A, I can get the base of the log, which in this case is 5. And I can raise it all to the second exponent, which in this case, I can raise it to what it's equal to, which is the second exponent. And that's going to be equivalent to what's inside the log, 7x. And I notice that it just becomes a very simple equation to solve. And I know that both of them mean the same thing, since all we did, we just did the property to rewrite log into exponentials. And this is way easier to solve. And at this point, it just becomes a very algebraic equation. So 5 to the second, so that's 25, equals 7x. To get x by itself, I need to divide it by 7. So now I know that x is equivalent to 25 over 7. And that's it. We have properly solved this logarithmic equation. Let's take a look at another example. Example B. Notice that what we're looking for is inside the log. So I need to get rid of the log. How can I get rid of the log? I can just express it as an exponential. Let me get the base of the log, which is 2. And let me have an exponent of what it's equal to, which in this case, it is 5. And now the exponential equation, it's always equivalent to what's inside the log, which in this case is 5 to the x plus 7. And again, these two equations, they represent the same idea. They're just written differently. But what's easier to solve? Definitely this one, because now 2 to the 5th, that's 32. So now notice that we have a linear equation, 5x plus 7. Let me solve for x. Let me get rid of this 7. So now that's 25. 25 equals 5x. Let me solve for x. By divided by 5. So now I know that x is 25 over 5, which is just equivalent to 5. So now notice that logarithm equations, they're not that hard. All we got to do is just rewrite them as an exponential equation and then just simplify until it becomes a little bit easier to manage. But now, by looking at example C, there's a huge difference between example A, B, and C. And that is that in A, there was only one log involved. B, there's only one log involved. And on C, there are two logs involved. So how do we tackle problems where there are multiple logs involved? Well, we still want to use this property. But in order that this property is true whenever we only have one single log, so we want to ask ourselves this question: is it possible for me to rewrite all the logs into one single log? In other words, can we condense the expressions involving logs? The first thing that you want to make sure is that they have the same base. So notice that the first logarithm has a base of 10. The second logarithm has a base of 10. So we're good. Now we can apply the property of logarithms to properly condense the expression. Well, notice that here we add in two logs. And according to the properties of logs, what I can do, I can just write it as a single log, where what's the inside of one log is multiplied by the inside of the second log. Let me just rewrite this as the log of 8x equals 2. And I notice that now they mean the same thing, because all we did, we just apply the properties of logs. But now I have it as a single log. And now that it's written as a single log, I can definitely use the idea of rewriting logs as an exponential, just like we did in example A and B. So let's do that. Remember that here, if we just write down log, it always has a base of 10. So I'm going to get the base of the base of the log, which is 10. And I'm going to have an exponent of what it's equal to, which in this case is 2. And that's always going to be equal to what's inside the log, which is 8x. And now we just solve this. 10 to the second, that's 100. So 100 equals 8x. Let me divide both sides by 8. So now I know that x is equivalent to 12.5. So that's another idea to keep in mind. Even though we have multiple logs, we can still use the properties of logs. But our objective is to first try to see if we can just rewrite the expressions using just one single log. In other words, can we condense the logarithmic equation? We got two more examples here. Over example D, regardless, notice an example A, B, and C. They were all using logs. So now this is our first example where perhaps we have a natural logarithm, or ln. So how do we tackle the examples where we have ln instead of logs? We approach it the same way. They both have base of e, which is good. So now I want to see if I can just rewrite this expression using one single log. Well, notice that I'm subtracting two logs. And my rule of logs says that if I'm subtracting, I can just divide the insides. So I want to get 4x plus 1 divided by the inside of the second, which in this case is just 3. And that's equivalent to 5. Now that I have it as a single ln, I can use the property of logs. The only difference is that ln has a base of e. But the idea is still the same. So I'm going to get the base of ln, which is e. So e, I'm going to make it have an exponent of 5. And that's going to be equal to what's inside the parentheses, which in this case is 4x plus 1 divided by 3. Even though this expression looks a little bit intimidating, we can definitely work this out, because e to the fifth is just one number. So let's find out what that number is for you to just convince yourself that it's nothing but a number. Notice that e, we have it here in yellow, so I'm going to press second ln, and that's going to give me the e expression to the fifth. It's a big number, but it's still a number, so I'm going to treat it as a number. Now, I don't want to just write down 1.48.41, because then I'm just going to ignore all the decimals that come before that. So I'm just going to keep working with the actual expression e to the fifth. So I still want to solve for x. In other words, I need to eliminate the 4, the 1, and the 3. The first thing that we should eliminate is the 3. Notice that it is dividing, so I'm going to do the opposite. So I'm going to multiply 3 to both sides. So now I have 3e to the fifth is equals to 4x plus 1. I want to solve for x. Let me get rid of 1. So minus 1 on both sides. Let me just continue it here. So now I have 3e to the fifth minus 1 equals 4x. I'm almost there. All I got to do is just divide it by 4. So now I know that x is equivalent to 3 times e to the fifth minus 1 all over 4. And this, it's an expression that we can definitely use our graphing calculator to find. So let's do that. Let's get 3 and let's multiply by e to the fifth. Let me close my parentheses. And I'm going to subtract 1 to it. So this is my numerator, 444.2394. And now all that, I'm going to divide it by 4. So now I have x is equivalent to 111.06. So regardless if it's ln or logs, the property still holds true. The only difference is that with ln, we're working with the Euler number instead of a 10. Under example E, notice that this is completely different than what we use, because now in example A all the way to D, all the ln's were on one side, either ln's or logs. But here we have a log equals to another log. So whenever we have situations of the form, even though it looks a little bit intimidating, this is actually one of the easiest way to solve. Because now, just like when we were looking at the same base formula, if I have 5 to the 2x equals 5 to the third, I can just eliminate the bases and have the exponents be equal to each other. That same property still holds true for logs. So if you do have a log equals to another log, and they have the same base, which notice that they have a base of 10, I can still cancel them out. And now I have 5x equals 2x plus 9. Again, if you have a log equals to another log and they do have the same base, you can cancel out the logs and just make the inside of each logs equal to each other. And now at this point, we can just use our algebra to solve for x. So let me subtract 2x. Let me subtract 2x. So now I have 3x equals 9. And if I divide it by 3, so now x becomes just 3. So this is how we can properly solve logs and ln's. But there is one thing that I forgot to mention through all these examples, and that is remember that inside the log, there is no negative value. So whenever we're solving for logs, we have to make sure that the value that we come up with, if we were to plug it back into the expression, we don't end up with a negative inside the log, which in this case, none of those examples do. That's why I think I just forgot to mention it as we were working on through problems. But every time you're solving for logs, you want to make sure, okay, I have a value. If I plug in this value back to the expression, am I going to end up with a negative inside the logarithms? And if you do, you ignore that solution. And if you don't, then we can acknowledge that as a solution. Notice that here, this 5, and if we plug it in here, we got 25. 25 plus 7, that's definitely positive, so we can definitely use this. 12.5, if I plug it into here, that's a positive, that's not a problem. 111, if I were to plug it in here, the whole inside the log is still positive, so we're good. And if I plug in 3, this is positive, so that's not a problem. We always want to verify that our solutions are valid within the domain. All right, so let's just discuss our last example for today, and that is when we have 3 different logs. So we have ln of x plus 1 minus ln of x minus 2, and that is equal to ln of x. Now we have 3 different logs, or natural logs. So how can we solve that? Well, take it one step at a time. Let's concentrate on the left-hand side. I'm subtracting 2 natural logarithms, so I can definitely use the property of logarithms, and that is saying that if I want to condense this, I can just rewrite this as the ln of the first divided by the second. And that is still equal to the right-hand side. With the right-hand side, it is still ln of x. Now I have ln equals to another ln. They have the same base, so they can just cancel out just like we did in example E. So now ln cancels out, so that's gone, and that's gone. So now I have the expression x plus 1 over x minus 2 equals x. And now this becomes an algebraic equation that we can definitely solve. So this x, I'm just going to put over 1. The reason why I'm going to put over 1 is because that doesn't change the meaning, but now I can think of this as if it was cross multiply. So I'm going to get x plus 1 times 1, well that's x plus 1, and that's going to be equal to x times x minus 2. So that's equivalent to x plus 1 equals x squared minus 2 of x. Let me take away an x, because what I want to do is I want to solve for x. So I want to make the equation equals to 0. So I have x squared minus 3x. Let me take away the 1. So now I have 0 equals x squared minus 3x minus 1. And that just looks weird, so I'm just going to rewrite it as this. It doesn't really matter if you put it equal to the left or equal to the right. They still mean the same thing. And now I want to solve this. X squared minus 3x minus 1. So we have different ways to solve quadratics. The first factor, can I find out two numbers that if I multiply it gives me -1, and if I add them up gives me -3? There's none. So unfortunately, we can use the quadratic formula. So we're going to get minus b, which in this case is -3, plus minus b squared, which is -3 to the second, minus 4 times a, where a is 1, times c, which is -1. And that is going to be all over 2 to the a, where a is 1. Let's simplify this a little bit further. So now we have that x equals 3, and that becomes 9, negative times a negative, so that's plus 4 all over 2. So now that becomes x equals 3 plus or minus the square root of 13 over 2. So now we have two solutions. I have the solution of x equals 3 plus the square root of 13 over 2. And I also have the solution of x equals 3 minus the square root of 3 over 2. Now, if we compute this expression using our graphing calculator, we're going to end up with x equals 5.10. And if we were to compute this expression using our graphing calculator, we would get x equals negative 2.10. So we got two solutions, apparently. And what do I mean by apparently? Because now let's figure out which one is true. I want for you to take a look at the value of negative 2.10. So if we let x be equivalent to negative 2.10, if we were to plug it in to this x right here, notice that we're going to end up with a negative value. And we know that that's not okay, because inside ln's and inside logs, we're not allowed to have negative values. So this is what we call an extraneous solution. We don't take it in consideration. Now, let's take a look at 5.10. So let me just erase that. So if we plug in 5.10 here, so if I plug it in here, notice that the whole inside is still going to be positive. If I plug in 5.10 here, 5.10 minus 2, this is still positive. So notice that we don't have negatives inside the ln when we set our value to be 5.10. So this is the only solution. Because remember that we're not allowed to have negatives inside the ln. So even though algebraically we get a value of negative 2.10, when we actually look at what's the result of using that value, we can see that it's an extraneous solution. So we just ignore it. We still have to test 5.10. And by testing 5.10, we see that we don't break that rule. So we just going to say that this is the only possible solution because it works out algebraically and it doesn't break any of the rules for natural logarithms or logarithms as well. And with this, it concludes our lesson for solving logarithmic equations.